So far, we discussed about Python programming language, error analysis, plotting, and non-dimensionalization. So these are setting up the framework for numerical schemes. So what I will describe in this course will be some of the schemes. Not all of it can be covered due to lack of time. So I will cover. So let's see how it flows. Okay, there are a lot of connections. So it is not that one scheme. All schemes are not independent; they are all connected. Okay, so that's one reason why I request you to pay attention. Uh, uh, Learn the essential of these schemes. You don't need to know the detailed prefactors, coefficients. That you can refer to the book, internet. But we should know what is the basic theme of that scheme. Okay, so we start with interpolation. Then after interpolation, we will do integration. Okay, so you'll see that there's a connection between interpolation and integration. Then we go to differentiation. After that, we spend significant time on ODE solvers, differential equation solvers, but it's called initial value problem. So like Newton's laws. So given the initial condition, you find the state of the system. Schrodinger equation is a initial value problem. Given the initial wave function, you find later. But anyway, Schrodinger equation is later. Okay, so here is particles, ordinary differential equation. Then we go to PDEs, partial differential equations. And PDEs will cover three methods. Spectral method, which is using Fourier transform. So I need to cover Fourier transform here. And finite difference scheme and Laplace equation. Then we'll also cover boundary value problems. Okay. Here, given the boundary condition, you solve the differential equation like string, taut string. So we have the ends fixed. It's not an initial value problem; it's a boundary value problem. And to solve these, we need this nonlinear solution of nonlinear problems. Okay, and bit of linear algebra I will do. So I hope Monte Carlo I won't be able to cover, and some of it I will have to rush. Okay, anyway, that's a plan of action. So we hope we can cover most of it in some detail. Okay, so let's start with interpolation. And it is said by some people that interpolation is mother of all numerical schemes. Okay, it looks very very trivial or rather routine things, but it is not. There are very interesting steps which are required for integration, differentiation. You'll see it. Okay, I mean I will show you that connection. Okay. Now, why interpolate? Let's motivate why we need to interpolate. So, in experiments or in numerical simulations, we get only limited information out of the system. By the way, there is a nature out here. I mean, there is nature, and we can make experiments or make measurements only at some positions, time, in space and time. So we get limited information, and from that limited information, you want to make extrapolation. So you want to construct a function which will fit through that data, and that is interpolation, really. Okay. Now, the example is weather experiment. We have very limited data points. Okay. For example, I mean, we need temperature and velocity, humidity, and so on. Now, this we can't measure at every point on the Earth. Some places are just inaccessible. Okay, in Antarctica, you can't go and measure every point. There are probes, but there will be very limited probes. Within a city, how many probes can we have? I mean, there will be 10-kilometer distance, oceans. So we get limited information, and from that we need to interpolate. For numerical simulation, we need all that data, and there will be interpolation used for that. Video transmission for TV. So the image is One thing is compression. The second thing is we don't want to send data at every pixel. We can give at some pixel, not at all pixels, and we interpolate in between. And gaming, gaming, high resolution picture will take too much time to compute. So the program will compute the values at some pixel and interpolate in between. Okay, now so the basic idea is the following. I just to recap. So we have the data points x0. These are the data points. So I'm doing 1D, one independent variable x and one dependent variable y. Okay, so y equal fx. So when you, like for example, we could have particle position, but we measure it in a 1D. So position at some times. So we have these blue circles are the data points. Okay, I measure it at some point. Now I need to construct a curve which goes through these data points, and this is my objective. Construct fx which goes through the data points. Okay, and this is interpolation. Now remember here, my curve needs to pass through all the points. That's the idea of interpolation. However, if I just too much data, in this case, there could be millions of data points, and we can't interpolate. I mean, if you think of a curve which goes through all the points, it is pretty. I mean, it's in fact wrong thing to construct a curve which goes through all the points. So, if the data is random and there are too many of them, it's best to do a fit through the point. Okay, and that's called regression. So I'm sure you guys have done linear regression. So we have a lot of data points, and you make a straight line which fits through the points. Or it could be also nonlinear function, but anyway, this is called regression. So these are two classes of numerical techniques. Given data, construct a function. In interpolation, the function passes through all the points, and in regression, it does not pass through all the points, but it passes through. We make a fit through the data point by minimizing error, and error measure could be different sorts. Okay. So I'm not discussing this here. I'm discussing this here. Okay. Now, linear interpolation. Let's just illustrate what is linear interpolation. So I have two data points, this point and this point. Okay. I want to know the value of the function in between. Of course, the function is this blue, green, black curve. But okay, I mean, I really don't know that function. But well, I'll make a guess that maybe the function in this band from this to this, it's a linear function. Okay, it's a guess. We don't know the function. So I make a guess, which is not really the black curve, but that's the best we got. So in essential, I mean, what you do in your classes is y minus y0 divided by x minus x0, right? So this is the point where I want to get the value x comma y equal to y minus y0 by x minus x0, right? So this is known to me. Okay, so given x, I can compute y by this equation. But it turns out in computer program, this is not very algorithmic. Okay, here this is good for your notes or for your hand calculation, but in computer program, I need to really give a very concrete instruction to the computer that okay, we compute this. In fact, this is rewritten. Okay, this is rewritten as following. So P2x, this is my notation. So one more point I want to say that f of x is approximated by a polynomial. Okay, so we are approximating by a polynomial, and number of points is written here, Pn x. So n is the number of points. This is the notation I am following, and it's followed in many books. So here I'm using 2 points. So this is the P2. Okay. Now we rewrite this expression. You can say that, you can see that this is exactly same. This one is same as that. So it is written like this. So all the function of x. So x minus x1 divided by x naught minus x1, this one, multiplied by y0, plus another function which is x minus x naught divided by x1 minus x naught into y1. Okay? So I'm making a clear segregation of what is x dependent and y dependent. So this is written as L naught y0, L1 y1. Okay. So L naught is a Lagrange polynomial. Okay. Lagrange polynomial. Okay. And this is same Lagrange who you seen mechanics. Okay. So this is by stalwart of mechanics. But in those days, in 1700, 1800, people were expert of many things: mathematics, physics, geometry, even social sciences. Anyway, so this is the same Lagrange. Now, 2 points we can get only linear function, but with 3 points. So here I have 3 points. So these 3 points. With 3 points, we can get a slightly more complex function. So we can get a quadratic function. Now it turns out, so I'm just going to write the expression here. So this function P3x polynomial, we can't do by hand. I mean, well, I mean, I can do by hand. You say y equal to a plus bx plus cx squared, like something like that. You write, isn't it? Now you have to compute a, b, c given the coefficients. So we have 3 equations and 3 unknowns. So for every x, that's what I will do by, if I were to do in by myself. I'm not Lagrange. So I have 3 equation y1, y2, y3 like that, right? So from 3 equations you find ABC. But that's not a good way to do it for computer. We write like this. So again, these are functions of x and is multiplied by y0, y1, and y2. And okay, it looks kind of okay. How do I get this function? Now, that's what I'll describe in the next slide. So we construct like this. So Lagrange polynomial multiplied by the data, y0, y1, y2. Okay. So formula is the following. So P and X is approximate function, please remember. With n data points, it's a polynomial. So we have Lagrange polynomial Lj multiplied by data value uh, at xj point. So yj is basically f, xj is yj. Okay. Now what is Lj? Okay, I mean, this is straightforward, except what is Lj. Okay. Now Lj is written as follows. It's a product function. This product, remember, everybody I'm sure knows about this. Product is just multiply this stuff. So for a given j, multiply for all i's except I equal to j. Okay. So we have xj minus xi here. Xj minus xi. And in the numerator we have x minus xi. Now let's do for 3 data points. So 3 data points, I want to construct L0 of x. What's the idea? So j is 0. This j is 0. So at the bottom, I'll have 2 terms. x0, let's just write x0, okay, 2. So x0 minus x1. So now i's are here, okay. So how many i's will be there? I not equal to j. So I can't have x0 minus x0. That is in fact goes to infinity, no? So x0 minus x1, x0 minus x2. So these are 2 i's, 1 and 2. At the top will be x minus x1, same. This I is same as this I, multiplied by x minus x2. So that is L0x. L1x will be what? So now put x1. x1 minus x0, x1 minus x2. And the top will be x minus x0, x minus x2. Okay. So we construct like this, and this for 3 points. For 4 points, there will be 4 polynomials, and there will be a product of 3 of these. Okay. Anyway, so this is, we can easily write a computer program for this, no? So these are very useful formulas for writing computer programs. And in fact, this is exactly the same as what I had in the earlier slide. And this is a demonstration how to construct these polynomials. Now, one important point to note that this one. So what happens to the important property that Ljxj equal to delta Jk. Now everybody knows what is delta Jk. It's a canonical delta function. This is equal to 1 if j equal to k, 0 otherwise. Now how do I get this thing? Now you can see by just structure of this function. So if I put for Lj, put xj. Okay, so Lj of xj, what will that be? So bottom will be is frozen, but top will be xj minus xi product. Okay, divided by xj minus xi. In fact, you can see that they cancel. They become 1. Each term is 1. So product of 1 is 1. But if you look at Lj of x0, what Lj of x0? So look at the numerator. So x minus, so first term will be x minus x0. Now I put x0 minus x0, which is 0. Okay, so you find that this is 0. Okay, unless j equal to so Lj xj is 1, otherwise it's 0. So that is the idea of this function. Lj xj is delta j. Okay. Anyway, if you are deriving a lot of expressions, this is useful to know, and this is interesting property. Now, error. So, what is error for? So, for this this approximation. So remember, fx is a function, and approximating fx by Pnx. Okay. So this is an important point. I really don't know the function, but given the numerical data or experimental data, I could only construct Pnx. Now let's see what is the error. So fx minus Pnx. So this we can derive it. I'm not doing the derivation right now, but we can derive this formula, and this is f. So nth derivative of f computed at zeta, which lies between x0 to xn minus 1. Okay, is some zeta. Okay, somewhere we don't know how to. Well, I mean, there exists a zeta. So this is this theorem does not tell you exactly how to find zeta, but there is a zeta in between, for at which you need to compute the derivative, divided by factorial n, and multiplied with the product x minus xi. So this is a product. So it's a product of n terms. So x minus x0, x minus x1, x minus x2, da da da, up to x minus xn minus 1. Okay. Now this derivation I'm not doing it, but you just believe me that this is the case. Now you can derive interesting stuff with that. One important result: if fx is a polynomial of degree n minus 1. So remember we have n points. Okay, so actually I should put we have this small n, no? Small n. So we have n points. So imagine that this function fx is some polynomial, okay, but degree 1 less than the data point. Then what happens to this derivative? So let's say n is 2. Okay. Now polynomial will be this will be 1. So it's a linear function. Now if I take linear function derivative twice, so what will I get as a result? So fn x, fn zeta will be 0 for this case. Right? So if f is n minus 1th order polynomial, then if you take n derivatives, that is 0. I mean, this is straightforward. Okay, so that means the error is 0. So this is 0. That means fx is Pnx. So my numerically computed polynomial is the correct, is the correct function fx. Okay, so there are some mathematical theorems. For example, the law of gravitation is 1 over x squared. So we know that we can deduce something that, okay, this function has to be of this nature. For somehow we get from physics or some law that if x is this stuff, then we have your numerical computation will be exact. So one important point is that all numerical schemes are not approximate. Some numerical schemes are exact. Okay, so this is an example. You can get exact results by numerical computing. I will show you some more examples a bit later that we can get exact results. Okay, some integration with computer will give you exact value. Okay, except round off. Okay, round off could be an issue, but otherwise you'll get exact values. Now, so this is one important result. We just derive it from this formula for error. Now, in general, this won't be the case. With n data points, fx could be, we don't know fx, it could be even larger or polynomial. So then how do I estimate the error? Okay, now that's a big problem. Okay, so now I will do that error estimation a bit later, after I illustrate by one example. So by the way, this is very easy to code. I'm going to share the notes with you. So this notes has this derivation. So I'm illustrating my Lagrange interpolation with a function fx equal to 1 by x. It's not a polynomial, remember? It's not a polynomial. So any polynomial I construct will be an approximation. Okay, there will always be some error. Okay, now we will construct from 2 to 5. I construct data at the intermediate points. So 2 to 5, right? So 2, 3, 4, 5. So let's say I construct only 2 data points, 3 and 4 x, and the value of the function is 1 by 3, 1 by 4. Right? So 2 data points only. Now this is a code. I think I can here there are 2 loops, j and I. So for this is constructing LJ. Okay, and after that I sum. So this part is constructing LJ. Okay, this part. And I multiply, so numerator by denominator. In fact, this is x minus xi, xj minus xi, this is lj, and I multiply by yj, and I basically, after this, I get the answer at a given x. Anyway, this is, you can just go through it, this is straightforward. So, this function will give us given x array and y array. It gives me the value at any x. So I can compute that any distance every x. So in fact, I'm going to insert x as a bin values. With lin space or a range, and I construct this polynomial. This is just straightforward. So I think I'm not going to spend time on how to write this code. You learned enough programming to be able to write this. Now let's see the result. Now remember, my data is discrete data from 2 to 5. So I do it, I compute it. Basically, I take some points sometimes, some more, all the points sometimes. So here, I take only 2 points. So at 2, which is 1/2, and at 5, which is 0.2. Okay. So here, the value is 1 by 5, which is 0.2. This 0.2 is just slightly above. Okay, this is 0.2 line. Now, my function is this, 1 by x. But with 2 points, what do I get by Lagrange interpolation? It's just a straight line. No, it's a linear function. Of course, this function, this straight line, is not same as the original function. So it's not a good approximation, but okay, I mean, this is the best we get with 2 points. I can take 3 points, which is P3, no? But 3 points, you have the choice. Which one should you choose? I can choose 2, 4, and 5. If I do this, then the line which is the red line is the P3x. Okay, the red line, this red line. Now, is missing this region. There is a problem. But this region, you can see that, well, for computer solution, this is not bad. Okay. My function, the dash curve, the black dash curve, is pretty close to red curve here. I mean, visually, okay, now there are errors, which I'm going to show in the next slide, but this is quite okay. But error is here. So you can see that if the data points are far apart, then interpolation will give error. So you should have data points reasonably close to each other to get reasonable function, reasonable interpolation. Now here, I again use 3 points, but 2, 3, and 5. With this part is okay, but this part you can see the red and black dash are not okay. They're not close. There's error. So this is the lesson we learn from by simple exercise, that choose points which are close by. Okay? Now with 4 points, I use all the 4 points, 2, 3, 4, 5. Then my curve is almost sitting on top of the black dash curve, which is exact curve. So error is least here with 4 points. Now you can compute those errors. So for this particular function, let's take only 2 points. No, I'm sorry, this is 2 and 5. 2.2 and 5. So error formula will be this, right? So product, no, it is sometime x minus xj f and zeta by n factorial. Okay, that is the formula for error. So this is a formula. Now this can be computed for a given x. Remember, error is function of x, no? So at given x, what is error? So it will depend on, like I showed you in the previous slide. For some x, error is less. For some function error is more. So it depends on the function. It is not same everywhere. Okay? In any case, so this is a formula. But problem, this can be computed. This can be computed. 2 is straightforward. But zeta is a problem. Now, how do I compute zeta? I mean, it's just too. We don't compute zeta. In this course, we don't compute zeta. So we make an estimate. So I'll find what is the maximum error for E2x. So what is the maximum bound on this E2 zeta? Now, and maximum bound on this. So let's find maximum error on E with 2 points. So it could be some x, you know. So in fact, we can figure out where is error is maximum. You can see the error is maximum at what point? I mean, if we have 2.2 and 5, error is maximum at the midpoint. You know, this is maximum at the midpoint. Of course, we don't know this value, okay, but error is maximum at the midpoint. And in fact, this is 2.25. Okay, just put x equal to midpoint, which is what, 3.5. Okay, and that's the maximum. Now, how do we estimate this one, f2 zeta? So this function is 1 by x. Okay, so I just compute twice. Actually, this is, I made a mistake. This is not correct. So this is x squared, and next is 2 by x cubed. So this 2 by zeta cube. 2 by zeta cube. Okay. So that is a maximum value of this. Now, what is maximum value of 2 by zeta cube? So remember, zeta can lie anywhere between 2 to 5. Zeta is somewhere, it's somewhere between 2 to 5. So 2 by zeta cube, where is the max? When zeta is smallest, and that is when zeta is 2. So this gives us 2 by 2 cube is 1/4. Okay. So so f2 zeta takes a max value at 1/4. at zeta equal to 2. By the way, so this is a maximum bound. Zeta may be somewhere here near 3. So I'll get f2 zeta to be 2 by 3 cube, which is less than 1/4. But I'm getting a bound on it. Okay? So this is called finding a bound on a calculation. So my error is bounded by 2.25, which is this product of this, divided by 2 into 1/4. So 2.28 by 2.25 by 8, which is 0.28. So error is basically bounded by this. Error will be less than this. So these are important. I mean, when I'm doing computation of wave function of some complex system, then I need to get a bound. I mean, how accurate is my calculation? Now we can plot these errors. Since I know the function exactly, so its function is 1 by x, and also I know p and x. So I can compute this for this particular illustration. So in real life, we don't know this function. Okay, so then we need estimate, but for this particular case, we know the error. So this for p2x is maximum at 3.5 is somewhere 3. No, maximum. Why it is not at 3.5? No, by the there's a factor p2 zeta. So this error. Okay, now this is not exactly maximum at 3.5. Is not here. Okay, is somewhere here. Okay, it is computed exactly from the formula. Now P31x is a green curve, so this is error is more here. The blue curve has error more here, and P4x error is pretty negligible. This is with 4 points, you can see the curve. It is pretty tiny. This one. So this is the best we can do for this particular problem. Now Python has, so one thing is to get all this homework done yourself. Other thing is to, well, don't worry about all this, but you can use Python's function. So it has a function called interpolate 1D. Okay, this is a good function, but it gives a basically pretty much linear interpolation. Okay, so it's a linear interpolation between two neighboring points. So the interpolate 1D with 2 points, of course, is a linear. That is, in fact, there's a green chain curve which is sitting on top. Now, here the green chain curve with 3 points. So there's one green chain curve here and one green chain curve here. So it's slightly tiny thing to here. But we get these two. So it's a piecewise linear. Okay. So there's a piecewise linear interpolation, interpolate 1D, which is good, is okay with when the points are close by. Okay. Here this piecewise interpolation. Here also this piecewise interpolation. Okay. Now, I mean, in Python there are more sophisticated function, but this is a simple one which we can use. Usage is very easy. So F is you can just first from SciPy import interpolate. Okay. So this part of package called SciPy. So SciPy has the interpolate package, and within interpolate there is a function called interp1d. Okay. Now you give X array and Y array, which is the data points Xi, Yi, and it gives the function F. Now to this function F, I can enter any value of X. If I enter value of X, then it will give me Y. Here I am entering an array, which is a linear array going from 2.1 to 5 with interval of 0.1. Okay, so it gives me value at, remember a range function, it is linearly spaced points from 2.1 to 5 with space of 0.1. Okay, it excludes 5, it doesn't include 5. And so P2 SciPy will be the value of the function here, and you can just do a plot. Okay, that's what I've done here. So let's quickly see how we can apply this technique to higher dimensions in 2D, 3D. So in 2D, we'll have the functions at the grid points. So these grid points, the function will be at these grid points. Now I want to compute function at any point in between. Like, in fact, imagine an image. I have image values only at discrete points, but I want to compute image value at intermediate points as well. So we can apply this Lagrange interpolation in the following manner. So my objective is to find the value of the function at here, x, y, this one. Now, of course, this is not lying on the grid point. It is somewhere in between. So now fix y. So I'm fixing y here. And I make this value of the functions at xi is, okay? So xi is vertical. Remember xi. Okay? So I have these values of the function at these grid points. Well, we don't know that value because values are given only at the grid points. But let's assume that these values are p tilde xi y. So p tilde xi y. Okay. Now, given that linear data points here, here, if for given y, I have the values, then I can interpolate not for given x. So this is the interpolation. Okay. I just apply straightforward Lagrange interpolation. So this is that Lagrange polynomial multiplied with the value of the function at given xi. But I don't know the value of the function here, but I know the value of the functions in the different grid points here, like that. Okay. So now I need to do second level of interpolation to get p tilde, to get this value. I need to get interpolation using the y coordinates. Now, so the next slide will tell you how to compute p tilde xi y. Okay. And so this is slightly, I mean, it's just straightforward. P tilde xi. Now I'm going along y direction. Okay. So see these yj's. So I estimate for given xi, for y, I just use this the vertical direction I compute it. So the Lagrange polynomial will be product of two polynomial x polynomial and y polynomial. Okay. So I told in a hurried manner, but we can easily see that. So we go first along x direction, but not at yi's, but at y's. But then we estimate these guys by going along y direction. So by basically the polynomial I construct is this. Okay. So Lij, now I have Lij, which is function of xy. And so this can be computed easily, no? Because I know the value of the grid points xi, yj. Okay, now we can do this for 3D as well. Okay, now please write a code for this. You can just take 1D function and you can do this for 2D as well. Okay, so with this I will stop my discussion on Lagrange interpolation. So splines, I want to discuss that briefly. So if a large number of points, so let's say we have 50 points or 100 points, then it's not a good idea to make a large degree Lagrange interpolation. So P50, a polynomial of 50 degree polynomial, will have a lot of oscillations. Okay? Now, it's not a good idea to have this kind of polynomials. So, in fact, we should not go beyond 5th order, 6th order polynomial for Lagrange interpolation. Now, so this is not a good idea. So the idea is to do piecewise interpolation. So let's say we have lots of points. So we have like this. Okay. Now I can do Lagrange interpolation to these 3 points. Then I do Lagrange interpolation to these 3 points, which is looking good actually. Then Lagrange interpolation to these 3 points. It looks nice, except there's no guarantee that the slopes are equal at these points, left and right slopes. Here it turns out, I mean, I chose the point slightly, it was a random point, but let's say, imagine I choose these points, these 3 points, and then points like this. So then there's a problem. I mean, these points like this, and the next point is next interpolation will be like this. So there is a problem. Its function is not differentiable. It's continuous but not differentiable. Okay. Now we want normally in physics, no, you want continuous and differentiable functions. Cusps are not good. So to avoid that, splines are used. So these are piecewise function and they are also smooth. Smooth means its derivatives are equal from both sides, differentiable function. Okay. Now I will only sketch the idea. I will not really go through the derivation. You can find that in the notes. We'll do cubic splines. So with the splines, the function the black curve, thin curve which goes through this is a spline, which is smooth function, which is differentiable at all the points. Okay, so we can look at the 3 points here, these 3 points. So you construct piecewise functions. So f0, f1, piecewise functions, which of course we had ascertained that the values of the function, this fx goes through the nodes. By the way, I forgot to tell that these are for nodes. Huh? So nodes, the fx must go through the nodes, and also it's differentiable. So the idea is that we start with piecewise function, but this is not fx. Huh? It's a double derivative of f prime. Okay, so we start with this and integrate twice. So it will be a cubic function. First integration will be square, then next is cubic, and so we construct piecewise function. This is function fi xi is between xi to xi plus 1, and this is xi minus 1 to xi, this function. But we have to make sure that whether this function will ascertain by construction that the nodes match, but also I have to make sure that the derivatives match, and that derivative matching condition leads to equations of this sort. Okay. Now these equations, these are unknowns. I don't know the double derivatives. Okay, but all these guys are known. Right hand side is known. HIs are the gaps which you take it to equal. For this course, we'll take this to be equal. Okay, HIs. Now, so we need to solve these double derivatives. Okay. Now that is a tridiagonal matrix, in fact. Okay. So we have a tridiagonal matrix. As I said, I'm going to rush through this, so I'm not going to tell you the details. But we need to determine this f double prime, and once I know f double prime, I can construct fx. But this function, once I construct them, is a smooth function. It's a differentiable function. Okay. So that's the idea of splines.